Hello everyone. Today we will be talking about correlation coefficients. This is a very important statistical analysis that we commonly use in terms of psychology and in terms of research situations. We find that in many situations researchers do tend to prefer using the correlation coefficient or using what we call a correlation statistic to analyze their data. And I'm going to be talking about the purposes of using a correlation statistic, what a correlation statistic does, how we calculate a correlation statistic, and then also different types of results that are associated with correlation statistics, and also its examination in terms of graphical representations that we may encounter in terms of our data. So first, let's begin with talking about the purpose of correlation of the Pearson product moment correlation statistic. Now, the purpose of the Pearson product moment correlation statistic, which is what we call our correlation statistic, examines the relationship between two continuous variables. Now, when we say continuous, what is it that we are talking about? Continuous variables mean that we have an independent variable and also a dependent variable that we assume can have any value that's along some underlying continuum. So for instance, in all our examples during the semester or in our previous lectures, I keep mentioning the idea that our independent variable has different categories. So we have the male and we have the female category. We have the high stress, we have the low stress category. But now we're changing it around to saying that your independent variable, your predictor, cannot be categorical in its nature or should not be categorical in its nature, but rather should be a continuous value. So in other words, it can fall on a number line, which is what we're talking about here. So our numbers really should not represent categories, but rather they should represent some aspect associated with measurement or assessment of a behavior or of some criteria that we're also examining our participants on. So here, think for example, height. That height can be any value that falls in a continuum. If you're considering inches, feet, or inches and feet, right? So if you were going to consider it to be decimal values as well, you can have height being represented in that way, weight the same way, age being represented in your years of age. So you are 18 years of age versus 19, 20, 21. So here we're not saying young versus old or a child versus an adult or an adolescent or anything like that, but rather we're saying these are your ages. So your 1 year of age, 2 year of age, 3 years of age. Your GPA also falls on the continuum, so it can be any value that falls on the continuum from 0 to 4. An exam score, all of these different things are going to really be continuous variables. So here, the purpose of correlation coefficient, so the use of our statistic of correlation, is really used to evaluate the relationship or the magnitude relationship between two continuous variables. So think of the situation where we would want to look at the relationship between height and weight, or GPA and a test score. So here we want to look at those relationships and ultimately ask ourselves the question, are there relationships between my independent variable and my dependent variable? And if there are, or if there is a relationship between these two variables, what is the strength of that magnitude? So in other words, how strong is that relationship? So is it a weak relationship? Is it a strong relationship? So in an ideal world, what is the Pearson product moment correlation statistic really going to tell us? It gives us a way of trying to, in a certain way, predict what it is that's going to happen in the future with my y score when I have my x value. So in other words, if I have my x value, my independent variable, can I predict my y value, my dependent variable, using that x value? So in other words, if you get a score of a 50 on the exam out of 100, can we then predict your GPA at the end of the semester? That's ultimately one of the things that we're trying to do, but ultimately the Pearson correlation statistic is looking at that relationship strength. So here, this is the prior step to that aspect of prediction. We're looking here at trying to determine what the strength of that relationship is. So ultimately, the Pearson correlation statistic is going to ask one of these following questions. How does the value of one variable change when the value of another variable changes? So is there a relationship or is there no relationship? Is there a pattern that exists when one value changes versus another value changing? Now, when we look at our correlation statistic or our correlation coefficient, which we also call our statistic a coefficient, our value represents the degree of relationship between these two variables. Now, our statistic in itself ranges from a -1 to a +1. Now, what does a -1 represent? A -1 represents a negative relationship. what does a negative relationship mean for us? Don't think here that that means it's a bad relationship or that bad things are happening. That's not what we mean here. All that we're referring to here is that the movement of our values are in opposite directions. So here, again, think of it in terms of this situation, that to use your correlation statistic, we need an independent variable, and we also need a dependent variable. Now, whenever it is that we put on a scale our independent variable and our dependent variable always goes on the x-axis. On the y-axis, we always have our dependent variable. So my predictor always goes on my x-axis. My criterion always goes on my y-axis. So here, since the independent variable is on the x-axis, this is my x value. The dependent variable, since it's on your y-axis, it's going to be your y variable. So here, if the IV is x and the dV is y, what we now want to look at is what is happening to the scores when we look at them in terms of their pairs. So if an x value goes up and a y value goes up, we are going to see that there is a positive correlation. What does a positive correlation mean for us? It means same movement. So what is that same movement? The same movement for direction. So here, if we have our scores moving in the same direction, in this particular case going up, we're going to have a positive score. What happens if my scores both go down? So my x score goes down and my y score also goes down. What happens in that particular situation? We're still going to have a positive correlation. Why are we going to have a positive correlation? Because again, we still have the same movement in terms of direction. So in other words, my scores are still moving in that exact same direction. So as x goes up and y goes up, we're going to have a positive score. As x goes down and y goes down, we're going to have a positive score. Now what happens in the case where we have our x value that goes down and our y value that goes up? Well, in this particular case, if we have opposite movement of our values, we are going to have a negative correlation or a negative relationship, just as we have here. So that's what a negative relationship refers to, that we have opposite movement. So we have opposite movement of our scores. So in other words, as x goes up, y goes down, or as x goes down, y goes up. So here, even if we find that as x goes up, but y goes down, in our particular case, we would still find that there is a negative relationship between our values, because that's what the aspect of negative and positive really mean for us in terms of a correlation coefficient. Negative just means that our scores are moving in opposite directions. Positive means that the scores are moving in the same direction. So again, if x goes up and y goes up, we have a positive score. If x goes down and y goes down, we still have a positive score. If x goes up and y goes down, negative. If x goes down and y goes up, we have a negative score. Now here, our limits are -1 and +1. Now here, if we look at the absolute value associated with my correlation statistic, the absolute value tells me the magnitude relationship between the two scores. So again, the absolute value, ignoring the positive or the negative sign, if we just look at how close my statistic is to a value of 1, again, it doesn't matter if it's positive or negative, the closer your statistic is to 1, that means the stronger the relationship, okay? The stronger the relationship. So in other words, if, for instance, we find that we have a score of a -1 in terms of my x and my y, it means that my x scores are going up and my y scores are going down, or x is going down and y is going up, but the strength of that relationship is very, very strong. It's almost it's a perfect actual relationship between them. So in other words, every time an x goes down, y went up, or every time that an x went up, y went down. In that particular case, we're going to have a perfect negative relationship. Now, what happens if we have a positive 1? That means that we have a perfect positive correlation. In other words, every single time that x went up, y went up. Every single time that x went down, y went down. So we have a perfect positive correlation in every single instance. So again, the closer your value is to an absolute value of a 1, it means the stronger the relationship. Now, the closer that your value is to a 0, let that be if you have a negative 0.1 or a positive 0.1 or whatever the case may be, the closer it is to 0, that signifies for us that there is less of a relationship, or if the value does become 0, it means that there is no relationship between your continuous variables. In other words, there's no pattern between the movement of my scores. So for some people, as x went up, y went up. For others, x went down, y went up. For other people, x went up, y went down, and it's all over the board. So here, there's no discernible pattern that we're finding in terms of trying to look at this relationship between our variables. Now, we're going to go through some examples here in just a bit. So again, here I'm covering the basics associated with correlation, and then we're going to move on to actually looking at this in practice. Now, here I've posted up for you again, one more time, your decision-making tree or your decision-making table associated with your statistical procedures. Now, for the last couple of weeks, we've really been talking about this aspect of testing a significant difference. So we've really been here. This is where we found the t-test, remember, that we were working with. So we talked about related samples t-test. We also talked about independent samples t-test when we had 2 groups, and then when we had multiple groups, 3 or more groups, we talked about one-way ANOVA. We also talked about factorial ANOVA. But now we're not talking about looking at differences. So if you remember back over here, looking at the relationship between variables, not looking at the difference between variables, looking at the relationship between variables is now what we're talking about. So here we're no longer going to be here in this area where we talk about looking at the differences between our scores, but rather we're going to be on this side. So what's the purpose of my statistical analysis? I'm looking at the relationship between my variables. So you'll notice here that now, once it is that we decide that we're going to be looking at the relationship between our variables, we're going to look at the type of data that we're going to be working with. So for instance, we're going to take measurements, right? So we're going to take people's heights, we're going to take people's weights. If you're going to be doing frequencies, you're going to be going down this direction here, and you're going to find statistical tests like chi-square. I'm not going to talk about that here, but here is really what we want to focus in on because we're taking measurements from individuals. So how many variables are you actually collecting? So what's the relationship going to look like? Are you only looking at the degree of relationship between 2 variables? If you're looking at the degree of relationship between 2 variables, now we want to look at what type of variables you're dealing with. Are they interval? Are they ordinal? And in our particular case, we're going to say that they are interval. So in other words, they may not have a true 0 value, but here we're going to assume that the differences between our values are equal in distance, and that the measurements actually mean something for us other than just solely rank. So here we're going to go down to where we say the Pearson correlation coefficient, which is our statistic of what we label as lowercase r. So if you guys remember earlier in our lectures, I never wanted to use the R to represent the range because I told you that the R represented our correlation statistic that we would talk about later on. Now this is where we're introducing that statistic of R in our particular case. So if we think to ourselves, or if we ask ourselves the question, what is really being asked by the correlation coefficient, or what's really being asked by the correlation test, the main question here that the correlation test is really asking us is the following question. Is there a significant relationship between my 2 continuous variables? Now here, the sentence that we continue to use this semester, which is the effect of IV on DV, still works. Now here, I never told you that you could only use this sentence if you were looking at group differences. I never mentioned that. So here, we still want to use this particular sentence, the effect of the IV on the DV. Now in this particular case, if we look at this particular sentence and we say to ourselves, well, is there a significant relationship between my 2 continuous variables? We can more specifically ask the question like as follows, now putting in some of our variables. Is there a relationship between height and weight? Now here, this is my research question, but if I state it in terms of this sentence, we would say the effect of, what's my first variable? Height, which is going to be my IV. So in other words, height on weight. Because weight occurs second in my question. So here I'm asking the question, can I predict weight using height scores? So, or is there a relationship between height and weight. So the taller that you are, do you weigh more or do you weigh less? The shorter that you are, do you weigh more, do you weigh less? That's really the question that we're trying to get at here. So ultimately, we want to make sure that we ask the appropriate question in our specific situation, because we want to make sure that we're asking the appropriate direction as well. That we're asking, well, what's the effect of height on weight, not necessarily the effect of weight on height, because my question really refers to the aspect of height and weight in this particular instance. But now if you wanted to change it up and you wanted to say, well, what's the effect of weight on height? You could also do that. It's still examining pretty much the exact same thing in those specific situations. Now here, let's look at our null hypothesis. What does my null hypothesis predict? Remember that your null hypothesis always predicts 0. It's always predicted 0 and it always will predict 0. Now what is it predicting 0 about? More specifically, if we look at the statement made by the null hypothesis at the initial points, now you'll notice that I'm using the term relationships. When we talked about t-test, when we talked about ANOVA, I talked about group differences. So I would always say no difference, no effect. Here, the null now predicts no effect, no relationship. That's the statement made by the null, no relationship. So in other words, my statistic that I would calculate in my study for my sample of individuals, which would be my R statistic, would be equal to a value of 0. But now remember, your null hypothesis and your alternative hypothesis are never stated in terms of sample statistics. They're always stated in terms of population parameters. Because again, like I've mentioned probably 100 times up to now, the purpose of us specifying a population parameter for the null and the alternative hypothesis is because the null and alternative hypothesis refer to the effects that exist out there in the real world. Who is the real world? The population is the real world, not my sample. So in other words, I need a population parameter that's associated with my statistic of lowercase r. What is my population parameter associated with lowercase r? That is my statistic of rho. So rho equals r. And here, I should have not written that because that's a p-value, sorry. Or that's my p. Rho, which looks like that, this is p. Sorry, yes, I know it looks very, very similar, and you're like, they look exactly the same. It's just the way that I am. I do apologize if I'm a little bit, kind of specific about the way I like to draw this. So rho, again, is that symbol. Rho is equal to r. Because remember that r is my sample statistic, rho is my population parameter. So if I know r, I know rho. So here, I'm going to state my null hypothesis in terms of population parameters. In this particular case, I'm going to state it with the population parameter of rho. And again, rho is spelled R-H-O in our particular case. So rho is going to be equal to 0. Because if you remember, r value equal to 0 signified no relationship. So if we look back on our previous slide, remember 0 indicated no relationship between my continuous variables. So here now what I want to do is I want to specify that rho would be equal to 0 since r should be equal to 0. Because my r value of 0 would indicate no relationship between my continuous variables. Now I'm just substituting my r for rho. Rho would then be equal to 0, which would indicate no significant relationship between my continuous variables. So here, if you want to set it in terms of the example that we're talking about in this specific situation, with the relationship between height and weight, the null hypothesis would predict that there is no relationship between height and weight. That the relationship statistic of r would be equal to 0, thus rho out there in the population, my statistic would also be equal to 0 in that particular case. Now, what does my alternative hypothesis predict? My alternative hypothesis is going to predict the alternative of the null, and the alternative is going to predict that rho would not be equal to 0. And I do apologize for that, guys. Would not be equal to 0. So in this particular case, we're now saying that r stat would not be equal to 0, that there would be a significant relationship between those values. Now, what is the significant relationship? So what is the statistic? I don't know what that number represents. That's why I never look at the alternative hypothesis in terms of statistical testing. I only look at the null hypothesis because the null gives me my 0 value. So remember, rho is my population parameter associated with my correlation statistic of r, and you'll hear from time to time people saying Pearson product moment correlation statistic, or Pearson product moment coefficient, or correlation coefficient, they all mean the exact same thing. They are referencing to this idea of lowercase r. And again, remember that rho is my population parameter. So what would the alternative hypothesis predict about the relationship between height and weight? It would predict that there is a relationship between height and weight, that there is a significant relationship between those two values. Now, when we look at correlation coefficients, there are different types of correlation coefficients, like I've mentioned already. So we talked about this aspect of positive versus negative. And again, just to make sure that we're all on the same page of understanding what the purpose of positive and negative refers to in terms of correlation coefficients, let's look at that here. A coefficient essentially indicates the direction of movement when the variable changes. So the value in itself indicates the magnitude of the relationship. The sign of the coefficient indicates the direction of that movement. So either is it going up or is it going down in terms of the relationship between x and y. So if variables change in the same direction or they move in the same direction, we're going to be talking about a direct, or what we call also a positive correlation. So here I wrote direct for you because many different textbooks use this idea of direct versus indirect correlations, but direct just really refers to positive correlation. What is a positive correlation value going to mean? Again, remember, as x goes up, we're going to assume that y goes up as well. Or as x goes down, y is also going to be going down in this particular case. So again, we have similar movement between x and y in both of these cases, so thus it gives us a positive value that we're going to be working with. Now, if the variables change in opposite directions or they move in opposite directions, we are going to be having what we call an indirect or a negative correlation. And again, remember, as x goes up, we would assume then that y would have to go down, or as x goes down, y goes up. So here, that's negative for you in both of these cases, because again, we have opposite movement occurring for both x and y in both situations. So now let's look a little bit at some types of correlation coefficients in terms of real world correlations that we actually examine. Now, whenever it is that we look at correlation coefficients and we look at real situations using correlation coefficients, we can first look at what happens at the x value, then look at the y value, look at the type of correlation coefficient that's going to be given to us, then the value itself, and then an example associated with the situation. So if we look at a situation where x increases, so x goes up, right? So we have movement of it going up, and y goes up in this particular case, we have a direct or a positive correlation. Okay, a direct or a positive correlation. What kind of values are going to be given to us in this specific situation? We're going to receive values that are between the range of 0 to a positive 1. And why between 0 and positive 1? Because remember, a 0 represents no relationship. So here we're saying, okay, it's probably going to be a 0.000001 to a positive 1. But here we would always be thinking of a positive value in our situation here. So here we would only be working with positive values. So think of a situation where we would have the time studying in terms of your exam performance. So time studying would be your x score. The exam score itself would be your y value in this particular case. So time studying is your x value or your x score. Your test score itself is going to be your y score or your y value. So here, the more time that you spend studying, the higher the test score. That's what we would assume. So we would assume that as x goes up, y goes up. We're going to have a positive correlation. So then, thus, you're going to have a value that is anywhere between a 0 to a positive 1. Now, what happens in the case where my x decreases and my y also decreases? So in both situations here, remember, we have equal movement in both situations here. We're still going to have a positive correlation as we did in our previous example. So our values are still going to range anywhere between a 0 to a positive 1. But if we look at a situation where this would happen, imagine as having less money in the bank means the less interest that you have. The more money that you have in the bank, the more interest you would have, right? So that would be in this type of situation up here. But here we're saying, well, you have less money, you're going to have less interest. So here again, money is going to be your x factor in this particular case. Interest is going to be your y factor in that particular situation. So again, both scores are decreasing, money is going down, interest is also going down. X increases in value, Y decreases in value. So here we have X going up, Y going down in this specific situation. We're going to have a negative or an indirect correlation that we're going to find between a value of 0 to -1. Okay, so our values now are on the negative side of the distribution. So the more that you exercise, the less weight that you should have. So again, remember, exercise in this particular case is my predictor, my independent variable, and my Y is my dependent variable or my criterion variable in this specific case. So the more that you exercise, the less weight that you should have. As X decreases in value, Y increases in value now. We're still going to have an indirect or a negative correlation. Our values still are between a 0 to a -1. Here, think of the less time that you have to take an exam, the more wrong answers that you're more likely to get. So again, in this particular case, the less time that you have to take the exam, or the time to take an exam, is X. The number of answers that you get wrong is my Y, is my criterion in this particular case. So in other words, if we speed up the process to take an exam, if we say you only have 5 minutes to complete 50 questions, you're much more likely then to get more negative or more wrong answers in that particular case. Now here again, don't think that negative and positive mean good and bad. That's not what this means in this specific case. If anything, here the example of money should demonstrate that to you, because here just because you have less money, you would think, oh well, that's a bad thing. Well then why isn't it negative? Well, because it's in reference to the direction of the movement of your scores. So less money, less interest. So here don't ever interpret the negative and the positive as being good or bad. That's not what that means in this specific case. All right. Now, just some general things to remember with the correlation coefficient. Remember, the correlation coefficient ranges from -1 to a +1. That's the maximum range of it, -1 to +1. You can never have any value that's beyond that. The absolute value of the coefficient in itself reflects the strength of the relationship. So again, remember, negative and positive don't mean good or bad. So don't think that negative and positive mean good or bad. So let's here look at this specific situation where we say, which one is a stronger relationship? -0.7 or +0.5? The answer is -0.7. Because again, remember, we're looking at the absolute value, so 0.7 versus 0.5, 0.7 is greater. The negative just refers to the direction of the movement. So in other words, as X went up, Y went down, or as X went down, Y went up. In this particular case, that we have a +0.5, we do have a relationship between X and Y. So as X went up, Y went up, or as X went down, Y went down, because they have the same movement. But we have stronger relationship, a stronger movement associated with -0.7. And again, remember, the negative and the positive don't mean good or bad. So don't think that in this particular case. Always think about it as being looking at the absolute value. That's what's going to indicate what's the stronger of the relationships. Remember that a direct positive relationship does not necessarily mean that it's good. It just means that there's a same movement between X and Y. And again, just having a positive value doesn't necessarily mean that it's stronger than having the negative value. Now, another important issue that we have to address associated with correlation coefficient is that outliers have a very strong effect on our correlation statistic and on the way that it's going to portray if we do have a correlation or not. Now, one of the things that the correlation statistic does take into consideration is it takes everyone's score into consideration. So just as we did with our mean, with standard deviation, and other statistics this semester, our correlation coefficient is no different in that it takes into consideration everyone's score. Since it takes everyone's score into consideration in terms of the calculation, and I'll show you the formula for it in just a couple of minutes here, we do see that outliers have a very, very strong effect, and they can potentially change a correlation from looking significant to not being significant, or it can take a non-significant correlation, something that's very close to 0 as a statistic, and then converting it to something that's a very strong significant correlation statistic, something that would be 0.6, 0.7. And here I'll show you just a couple of those examples in just a couple of minutes associated with how outliers could potentially make that kind of effect. Because remember, if we're taking an example such as height and weight, the relationship that we would expect, or the typical relationship that we expect between height and weight, is that the taller you are, the more that you weigh, because there's more mass there. The shorter that you are, the less that you're supposed to weigh, but there are exceptions to those. There are people who are very tall who do not weigh very much, and then there are people who are very short who do weigh quite a bit. So in those particular cases, those individuals don't seem to fit into the schematic of what we would assume to be the pattern of height and weight's relationship, but yet they still are going to be included in our analysis because we're still going to be gathering their data. Or even take into consideration somebody who says, well, I studied 8 hours, I would expect to get an 80 on the exam, but a person who studied 10 hours ends up getting a 40 on the exam. And there may potentially be other factors that may be contributing to that dependent variable score there, but we would still have to use that person's score into the calculation because we're not going to be holding them out just because we don't like the way that they look. Because here the idea behind a correlation is that you really want to look at that relationship using as much data as you possibly can to draw those kinds of conclusions. Now I'm going to show you the formula here for correlation coefficient, and again, if you're thinking at this point, nope, I'm good with correlation coefficient, I really do not want to deal with this in any capacity. Again, remember that especially for something that's as long as this, like with T, with F, and also with correlation statistic, these statistics are actually quite extensive in terms of their calculation. So rather than us actually doing this in terms of the exam or on a homework assignment or anything like that, here I'm going to work through a problem using this formula, but I'm not going to require you to do this in terms of the exam or anything like that. So if I were to ever give you a question in terms of correlation, I would give you the statistic itself, but not necessarily how do you calculate the statistic. Because again, more than likely, if you're ever going to use these kinds of statistics, you're more than likely going to be using them using a data analysis software such as SPSS or SAS or to some other statistical software package that you would use, even something like Excel. So in reality, we're not going to spend too much time talking about how to actually calculate it, but I do want to go through the calculation of correlation coefficient just to show you in case you ever do want to do this by hand. Now, our correlation coefficient, just as all our other statistics, again, is made up of effect variance in my numerator, and in my denominator, we have error variance. Now, in this particular case, how do we know that the numerator is effect variance? Because we're looking at the relationship between x and y. And that's really what's of interest to us, is examining that relationship between those two factors. Now, if you also notice down here, in terms of our denominator, we have variability, or the way that we would define variability in this particular case, through error variance. This is the way that the formula describes it for us. Now again, this is very different in terms of the calculation of the way that we saw for the T formula, in terms of the way that we saw for the ANOVA formula. All these formulas are different because they use different terms to be able to use in their calculation, but yet theoretically the underlying concept for all of those formulas boils back down to this idea of effect variance divided by error variance. Now here, if you're looking at this formula and again you're just like, nope, I'm not even going to try following along with this, I'm going to go ahead and skip this part of the lecture, I would recommend not skipping this part of the lecture because it's just good to kind of see how it is that I actually do this calculation. And if you actually notice, there's nothing really complicated here in terms of this formula. It just looks like a lot of symbols, but if you work slowly through the symbols, you're able to really identify that we've already worked through all of this stuff in the past, and in reality, there are no other formulas that you have to use in terms of the calculation of any of these numbers. The most complicated it's going to get at this point, to be honest, is going to be the squaring that you're going to do of your x values, and also that you have to take the product term of x and y. So in other words, multiplying x and y to get your product term here. So if we look at here at our data, let's say for instance again, we're going to be looking at something like height and weight score. So let's assume that this would be something like our height score. Let's assume that this would be something like our weight score. We want to look at the relationship to see if there is any relationship between these factors. So you'll notice here that not in every single instance we see the same pattern. So in some instances, x is like a 2, y is a 3, x is a 4, y is a 2. So as x went up, y went down. As x went down, y went up. So you'll see that there's a lot of different patterns that we have here to our data, because this is the reality of the way that our data is going to look like whenever it is that we actually collect these numbers out in the real world. It would be awesome if out in the real world, every single participant functioned the exact same way as everybody else. As x went up, y went up. Or as x went down, y went down. Or as x went up, or as y went up, x went down. Whatever the case may be, that would be an ideal situation for us. But in reality, that's probably not going to happen. So again, here you'll notice that the formula in itself of correlation coefficient is really not that complicated. There's just a lot of steps to it. And just like we did with our t-test and also with ANOVA, there's just a lot of steps to the process of inferential statistics. That's why most of the time we actually don't do them by hand. But here again, like I mentioned, I do just want to go through one example by hand just to demonstrate to you how it's done. So again, if we have our height and our weight values here, our height would be our x values, our y would be our our x values would be our height, our y values would be our weight. Remember that x corresponds to my independent variable that we'd be working with, that's my predictor, and y in our particular case would be my dependent variable that I'm working with. So in this particular case, we notice that our values are 2, 3, 4, 2, 5, 6, 6, 5, 4, 3, etc. And again, like I was saying, in an ideal world, we would really want for everyone's scores to always have the exact same pattern. As x goes up, y goes up, or as x goes down, y goes down, or x goes up, y goes down, or as x goes up, or x goes down, y goes up, or whatever the case may be. Any pattern that you really want, right? It would be ideal if everyone demonstrated the exact same pattern, but in reality, that's not going to happen for us. Rather, what are we really going to be seeing? We're going to be seeing scores that are all over the place. Some people's x goes up, others y goes down. For others, x goes up, y also goes up. So we're going to see all these differences that we're going to find. So what we want to find is we want to know what is the magnitude relationship between height and weight. That's really what we want. So we want to know, what is my correlation statistic? That is the major question that we want to address in this particular situation. All right, so the first thing that we really want to do here is, since we already know our x and our y values, the next thing that we want to do is we want to try to take our squared value, since that's what we're going to need in this particular situation. So you'll notice here in the denominator, we need to know what my square is for all my x values, and then I also need the square for the y values. So what I want to do is I want to go ahead and square each one of my x values and then square my y values, so that way I can go ahead and have those. So in our case, 2 becomes 4, 4 becomes 16, 5 becomes 25, 6 becomes 36, 4 becomes 16, 7 becomes 49, 8 becomes 64, 5 becomes 25, 6 becomes 36, and last 7 becomes 49. So we're done here in our particular case for squaring all our x values, because you'll notice that we don't need to square x here, we don't need to square y there, we don't really need to do that here nor here, but rather we need to do it in this particular case in both of these situations in the first part of our denominators for each one of those brackets. So now we're going to go ahead and do that for the y. So 3 squared is 9, 2 squared is 4, 6 squared is 36, 5 squared is 25, 3 squared is 9, 6 squared is 36, 5 squared is 25, 4 squared is 16, 4 squared is 16, and last 5 squared is 25. So in our particular case, we're done now with the squaring portion associated with our formula that we needed to have in this case. So we already know what our x values are because we have that column. We already know what the y values are. We have those in that column. We now have our x squared columns. We have those in that column. Our y squared values are in this column here. So now the next thing that we need, you'll notice, is what I circled here. That's this product between x and y. So in other words, multiplying x and y. So in our particular case, now we're going to go ahead and do that, which is going to be in our last column. So 2 times 3 is 6, 4 times 2 is 8, 5 times 6 is 30, 6 times 5 is 30, 4 times 3 is 12, 7 times 6 is 42, 8 times 5 is 40, 5 times 4 is 20, 6 times 4 is 24, and last 7 times 5 is going to be 35. So now we have, in our particular case, everything that we really need to work with our formula here. The last portion that you really do need, that I guess we haven't talked about until this point, is really the n. So again, this in this particular case is going to be our sample size, or in our particular case, pairs of x and y's. So in other words, we're going to treat this as participant 1 and participant 2, participant 3, and we're going to go all the way through, and we should have 10 participants in our particular case. Now, what happens in the case where participant number 1 gives us an x value but not a y value? Then I wouldn't be able to use that person. Or what happens in the case where a person gives me a y value but not an x value? I cannot use that person. The way that correlation coefficient works is that it needs those pairs of value. It needs the x and it needs the y from every single participant. If we don't have both from everyone, it's not going to work. All right, so now let's go ahead and work on our formula. So in our particular case here, we want to go ahead and begin to work on our formula, and we are going to work with our data in this particular instance. So I have here the formula for you again as we had on the previous screen. So remember that n equals 10 in our particular case because that is our sample size. So the way that our formula is going to go, and here we're going to go step by step. We'll first begin with the numerator, our value of 10 times the sum of the product term of x and y. So we already have the product of x and y here in my last column, but now I would really want to do the sums, right? So I need to do the sum of x and y, I need to do the sum of x, the sum of y, I need to do the sum of x squared. I also need to do the sum of y squared in our particular case, so summing up all of those columns. So I've gone ahead and already done that for you. So the sum of x is equal to 54, sum of y is equal to 43, the sum of x squared, so in other words, squaring all of our x values to create this column now gives me a value of 320. Remember, this is different than this portion right here. So this value is not this value right here, because remember, the sum of x squared, which is that, is the summing up of all our squared values. The sum of x squared is then summing up this column and then squaring that value. Now y squared, our sum of y squared is going to be 201, and last the sum of x and y, so that product term is 247. So now we have all our pieces of the puzzle that we need in our particular case. So now I need to know the sum of x and y of that product term, which is again is 247. There we go. Minus 54, which is the sum of x, times the sum of y, which was equal to 43. And now our denominator is going to look like the following. So we are going to have in brackets 10 times the sum of x squared. So we already know what x squared was, and now we're just going to go ahead and take the sum of that. So we already knew what all our x values were squared. We added those up. That gives us a value of 320 minus 54 squared. Because remember, our sum of x in our particular case was 54, and now we're squaring that value, because remember the sum of x is what's in parentheses first, and then we do what's outside of the parentheses second. So in our particular case, 54 squared, close the bracket off there, times 10 times, in this particular case, 201, minus the sum of y squared, which would be equal to 43 squared. And we're going to go ahead and take the square. And the last part of our formula here is going to be to take the square root of this entire denominator. So here we're going to go ahead and continue working with our information that we have here. So 10 times 247 is going to equal 2,470 minus 54 times 43, which is going to equal 2,322. And the difference between those two numbers is going to be 148. So there's my numerator, 148. That's what my numerator is going to be in our particular case. So now let's work with what's in brackets. 10 times 320 is going to equal 3,200 minus 2,300, which is going to be 54 squared. So 54 squared is going to equal 54 squared is going to be equal to 2,916. Sorry, I made a mistake right there. You see, that's why I wanted to double check my math. So let me go ahead and just erase that really quickly here for you. There we go. And here, as you'll notice, and some of you had made these comments before, whenever it is that we are working through this formula, is that one of the comments that you make is, man, if we make one little tiny mistake, we're done, like everything is spoiled. And you are absolutely correct. And that's always the rough thing whenever it is that you're working with these formulas. And that's why normally we don't spend time actually doing this stuff by hand, because it's very easy for us to make a mistake. So 2,916 is 54 squared. And now in our particular case, that's going to be one of our brackets. Our next bracket is going to be 10 times 201. So that's going to be 2010 minus 1849, which is going to be 43 squared. So now 3200 minus 2916 is going to give you a value of 284. So that's our first bracket here, 284. And our second bracket, 2010 minus 1849 is going to be a value of 161. So now 161 times 284 should equal a value of 45,724. And now remember, we still need to take the square root of this value. So if you're like, wow, okay, that seems totally wrong, remember you still need to take the square root. So the square root of 45,724, and I'll do it over here. So the square root of 45,724 equals 213.83. All right, so that's my denominator in my formula. So I know that my numerator is 148. Divide that by 213.83. So again, 148, divide that by 213 is going to equal a value of positive 0.69. Now remember, I told you my value of correlation coefficient should range anywhere between -1 to +1. So my value that I calculated, my statistic that I calculated, confirms that for us because it does range within that specific, between that -1 and +1. Now, if I would have got something above +1 or something less than -1, I would have been a little bit scared at that particular point. So here we've gone ahead and confirmed that our statistic is now 0.69. So we're pretty happy, right? So now we want to know, now what, right? I guess that's the big question. So great, we've done all that, and again, our value is 0.69. The big question is, now what do we do? And the answer to now what do we do, we come back to our favorite thing that we've always been doing all semester long, null hypothesis significance testing. And I know that you guys again are like, I thought we were really done with null hypothesis significance testing. I told you we weren't. I told you until the very end of the semester we would continue to use null hypothesis significance testing. Here it is again. So now what we need to do is we need to go through and we need to find the critical value that we're going to use for our specific sampling distribution where the null hypothesis is true for the R statistic. So we need to use our critical value sheet, and I've gone ahead and posted up a critical value sheet for you on Blackboard so you can go ahead and follow along using that critical value sheet and be able to find the values that we need. So in our particular case, we need to use the critical value sheet to be able to find my critical value so I can identify where my region of rejection begins. Because remember, just as we did with our T statistic, just as we did with our ANOVA statistic, now here what we're trying to identify is my statistic significantly different from the value given to me by the null hypothesis? Because remember, what does the null hypothesis predict? The null hypothesis predicted that your R value, or rho as our population parameter, should have been equal to 0, but rather your value did equals 0. So rather here what we need to do is we need to know, is my statistic of 0.69 significantly different from that 0 value? So in other words, is it extreme enough for me to conclude then that there is a relationship between my X values and my Y values in terms of their pattern? So here, what do we need so that way we can come to a conclusion of what my critical value is going to be? I need to first know what my N is, or my sample size, because I need to be able to calculate my degrees of freedom. Degrees of freedom in this particular case for my R statistic is going to be equal to the number of pairs minus 2. So we're going to take one value from the X column and one value from the Y column. So thus you end up taking minus 2 in this particular case. So remember, in our case, we had 10 pairs or 10 participants. We took 2 because again here now we're dealing with 2 scores in this particular case. So we are now going to have degrees of freedom equal to a value of an 8. Then we have to pick if our distribution is going to be a 1 or a 2-tailed test for our significance test, because our distribution for the R statistic is actually normally distributed. So the mean of this distribution is going to be equal to 0, and it's going to have a positive side and also a negative side of the distribution. So we want to be able to identify if my statistic lands in that region of rejection or not. So my distribution looks just like the one where the t-value distribution and also the z-value distribution, that it has a mean equal to 0. So I now need to locate on here the regions of rejection. So where are the regions of rejection? I need to do that using the critical value. The last portion that I need to be able to identify where the critical region is, for the purposes of finding my critical value, I need to find my alpha level. What is my alpha level? I'm going to set it at the maximum value of 5% because remember, I want to try to maximize power. So here I want to try to have the most powerful test that I can. So I'm going to keep my alpha level set at 5% or at 0.05. So in this particular case, we are going to want to use a critical value table that looks just like this. And again, this is the same one that's posted on Blackboard for you, so you can go ahead and take a look at that one and follow along as well. So we can see that going down vertically, we have our degrees of freedom. And again, it tells you right here how to calculate your degrees of freedom. So n being our number of pairs or our sample size minus 2. So in our case, it was 10 minus 2. So 10 minus 2. Remember that my alpha level was set at 0.05. And here I want to be a little bit conservative and I want to do a two-tailed test. And why do I want to do a two-tailed test? Well, because I want to make sure that I catch my statistic in the opposite direction just in case it goes in that opposite direction of what it is that I predicted. Now remember that our statistic was a positive 0.69. So we want to know, does our statistic land in the region of rejection or not? So here you'll notice that we have level of significance for a one-tailed test, two-tailed test. I've already told you it's a two-tailed test that I'm interested in. So I want to look at this column here or this section. And then remember that your alpha level in this particular case is set at 5% or 0.05. So here we go ahead and find our alpha level of 0.05 or our 5% for 8 degrees of freedom. And we go ahead and we just follow along. And we're going to come across and we're going to find that my critical value is going to be equal to a 0.63. Now remember, this 0.63, since it's a two-tailed test, has to be positive and it also has to be negative. So it's got to be both. So on my distribution that I'm going to draw for my R statistic is going to look like the following, where my mean is equal to 0. And now my critical value is going to be set to the right and also to the left. So here to the right is going to be positive 0.63. And to the left is going to be negative 0.63. So now we have to go and we have to find, where does my statistic of 0.69 land? And remember, it's positive 0.69. So it lands just right here. So there's positive 0.69. So positive 0.69 lands in this particular case in the region of rejection. So in our particular case, we are going to go ahead and we're going to reject the null hypothesis. And why are we going to reject the null hypothesis? Because my statistic landed inside of the region of rejection. So here, in terms of the relationship between height and weight, based on our data, we conclude that there is a significant relationship. And that relationship almost has a magnitude value of 0.70, so positive 0.70. In other words, as x goes up, y goes up. And also as x goes down, y goes down as well. So we see that pattern in our scores, and that's why we see this particular statistic of positive 0.69 being given to us. Now, how are we going to format our statistic? Our result is going to look just like as we have here. Our statistic is going to have my R value. My R value is given to me, sorry about that, guys. My R value is given to me in italics, and my P value is also given to me in italics. So I write R equals, and it's lowercase r, never capital R. Capital R is used for some other statistics. Here in our purposes, we're going to use lowercase r. R equals positive 0.69, comma, P value less than 0.05. So in other words, since our statistic landed in the region of rejection, I'm comfortable with using the P less than 0.05. So the probability that my statistic of 0.69 occurred solely due to chance is less than 5%, and that is enough for me to be able to reject the null hypothesis. So remember, we reject the null in this particular case. Okay? And why did we reject the null? We rejected the null because our statistic landed inside the region of rejection based on our degrees of freedom, based on our alpha level, and also based. So again, we're comfortable making that conclusion at this point. So now let's look at this aspect of trying to identify correlations whenever it is that we encounter graphical representations. Now, the figure that corresponds to the use of a correlation coefficient is what we call a scatter plot. Now, typically whenever it is that you're looking at group differences, you may use something like a bar graph or you may use something like a line graph. And when you guys take research methods later on, you'll learn about how to use and construct those particular types of display or effects displays. But in our particular case here, I do want to just kind of introduce this idea of a scatter plot because this is a very common figure that we use to be able to look at our data in terms of correlations. Now, whenever it is that we look at our scatter plots are actually very good to indicate for us what kind of correlation statistic it is that we're dealing with. So even though we may not be able to calculate the specific statistic at that time, or we may not know what our statistic was at this instance, using a scatter plot is actually very indicative for you of what kind of relationship exists amongst your data. Now here, for instance, I've given you an example of a direct or a positive correlation, and what we find here is that, again, remember, this is my x, this is my x-axis down here, so this is going to be my predictor, my IV temperature, and then here is my y-axis, so this is a little bit of an interesting, scatter plot in this instance, that we look at the temperature and its correlation associated with beer being sold. And what we find here is that temperatures rise, we find that more and more beers are being sold. So as X goes up, Y also goes up. So you'll notice that as X is going up, Y is going up. This is going to mean that we have a direct correlation or a positive correlation. Because as our values in X continue to increase, we see that our values in Y continue to increase. Now here, how do we plot out this data? Again, remember, we have pairs of data points. So in other words, we had to get the temperature and the beer sold on this specific temperature, at this specific temperature, and at every other point in time. So in other words, when it's 20 degrees, we know that it's about 15 beers being sold because we had to get both data points. If we don't get both data points, I can't plot out my data. Now here, you'll notice now that we look at the relationship between coffee sales and temperature, and we find here that we have a negative relationship. So as temperature begins to increase, we start seeing that there's a decrease in coffee being sold. So again, remember our x-axis and our y-axis here, and what we find here is that X increases in our particular case, we find that Y decreases in our particular situation, thus giving us a negative or an indirect correlation that we would find, because again, we see that as temperatures continuing to increase, we see decreases in terms of coffee being sold. Now here are just some other representations of what you would expect to find if we were to ever have correlation scatter plots given to you. Now here I give you four different types of correlation scatter plots, just so that way you can be able to identify them at later points in time. Now the likelihood of all of them, of your scatter plots looking just like the ones I've given you here, is highly unlikely, but you may see something that's similar to this, thus leading you to conclude what the relationship may look like. So on the exam, it would definitely be feasible for me to give you a scatter plot and ask you to tell me what kind of correlation it is that you're dealing with. So is it positive, is it negative, or is there no correlation between our variables? So in our particular case here with letter A, you'll notice here that we have what's called a negative or an indirect correlation. So again, as our values on X continue to increase, we see decreases in our Y values. And here you'll notice that we drew a line through our data points. Now here we could do that through all of our graphs, through all of our circles here that I've drawn for you. And what we find here is that to the best of our abilities, we try to fit our data as best as we can through all of our data points. This is actually what's called a regression line, or what we also call the best fitting line. And this is a very common procedure or practice used whenever it is that we're dealing with scatter plots. The idea of this regression line or this best fitting line is that we try to fit a line that best fits through all our data points. In this particular case, you'll notice that all our data points land right on this line that we have right here. So in this particular case, since all our data points land right on this line, we would expect then that we would have a perfect correlation. Now, the more that our scores deviate from this best fitting line that we've created, we're going to find that our correlation coefficient is going to become weaker and weaker and weaker. So in other words, it's going to get farther and farther away from a 1 and start approaching more towards the 0 value. because here it's assuming that if I'm trying to fit this line that best captures everyone's data points, and the more dispersed we are away from each other in terms of our data, in terms of our values, if we don't show that same pattern in every single instance, then we're going to expect then that we're going to see these smaller relationships, because the more spread out that everybody is in terms of both of their scores, in terms of their X and Y's, we're going to start now seeing that there's going to be less of a relationship amongst that pattern. So here, what we would really like to see in every single instance is, do we have a perfect correlation in terms of it being a -1 or a +1? Now here, this is a +1 negative correlation. What is a +1 going to look like? A +1 correlation is going to look like the red line. So this blue one's our negative correlation. Our red ones are positive correlation, because again, remember with the red one here, as X goes up, Y also goes up. With the blue line here, as X goes up, Y is going down in that particular case. So we would love to see in every single one of our results, if we were to look at the relationship between X's and Y's, we would love to see everyone's data plotting exactly the way it is right here, because that would make everyone's job very, very easy. But in reality, that's not going to happen. Now here in the next figure that we have here, letter B, you'll notice here that we have a no correlation. So there's no pattern to the relationship here. Our correlation coefficient is at a value of 0. So in other words, some people's scores are going up on X, others are going down on Y, others are going up on X, others are going up on Y. X is going down, Y is going up, X is going down, Y is going down. So they're all over the place. So since everyone's kind of not showing this pattern of what that systematic pattern, what we would expect, we start seeing that there's a value closer to 0, and in this particular case there is no correlation. So our scores are all spread out all over the graph. In this particular case now with the C distribution, or C figure, we start seeing here that again there's a correlation between our data, and in this particular case we draw that circle going towards the from left to right, so going higher, with our best fitting line going through all our data points as best as we can. So again, it's a line, so we're not going to have a squiggly line, let's not connect the dots, but we're going to go with the best fitting line, trying to capture as many of those data points. But now you'll notice here, in contrast to the one that's in letter A, there's no deviation of our data points from the line. Everyone is showing as X goes up, Y goes down in every single instance. Here, we're not always seeing that pattern. In some instances, X may go up, Y may go up. In other instances, X may go up, Y may go down, thus creating a little bit of that deviation from the line, thus creating still a strong correlation, but it's a little bit weaker in its nature. Now, our last figure here that I have for you is this figure that we have a weak correlation. So you'll notice here that our scores are spread out quite a bit, but yet they're not as spread out as we have here. So there's still some spread, but there's still some direction of movement that we have. It almost looks like if our scores are going from higher X's, lower Y's. So we start seeing a little bit of that pattern here, thus giving us a negative correlation. So you'll notice that this value is weaker than this value here, because it is a 0.4 versus a 0.9. And that value there of a 0.4 is weaker than this value of a 1, thus showing that we have a little bit of a weaker correlation. That strength of that relationship is not really that present here, so it's a little bit weaker in its nature. Now, the last figures here that I want to show you are these figures associated with our outliers. Now, again, remember that our outliers, in our particular case in certain situations, may potentially create a result that may fabricate data for us and may create an effect that really is non-existent, or it may even wash away an effect as well. So you'll notice here we have both the exact same figures. The only difference between both figures is that one of the figures, the one on the right, letter B, has our outlier included on the top right-hand corner, and letter A over here does not have it. So you notice that if we were to try to draw a line through letter A, through all our data points to the best of our abilities, we would probably do something along this direction, probably. So it gives us a negative value, but that's very, very close to 0. Scores are very, very spread out amongst each other. There's a lot of deviation from this line. There's no real discernible pattern that we identify here. As X goes up, Y goes up. As X goes down, Y goes up again. So there's no real pattern here to our data. But now here, including this one outlier, you'll notice that now the shape that we have to draw has to capture all those data points. We just can't say, well, we're not going to capture it. But here we have to capture that data point. So now if we draw this best fitting line through all our data points, We draw a line that goes like that. So now you'll notice that more and more of our data points are now starting to approximate this line, and it's all being driven because of this one single point that we have up here. So you see that this value is an outlier, but yet it's creating this very large effect. So it actually takes your correlation statistic from being very, very close to 0 to now being very, very close to 1. So you'll notice here that we do see those potential effects in these particular situations. So now the last thing I want to present to you in terms of our lecture for correlation is, what does a correlation coefficient actually mean? So what is a large correlation coefficient? What is a small correlation coefficient? So if you didn't know the p-value, so in our particular case here that we don't know what the p-value is associated with this statistic right here of 0.85, is that a large? Is that small? What does this really mean for us? So just to give you some kind of basic standards associated with our correlation coefficient, I want to do the following for you. So remember that your correlation coefficient is a numerical index of the relationship or the correlation between our two continuous variables. So in other words, remember that the higher the value is, independent or regardless of the sign, so the absolute value, the higher that value is and closer to 1, the stronger the relationship. Now, once it is that we add in the positive or the negative, then that suggests what the direction of the relationship is. So let's say that we have a -9 or negative 0.9 versus a positive 3 or 0.3. In that particular instance, the negative 0.9 would be a lot stronger relationship, indicating that there's different movement. So in other words, as x goes up, y goes down, or as x goes down, y goes up. That's a stronger relationship, right, than viewing what we see with a positive 0.3, that we see as x goes up, y goes up, or as x goes down, y goes down. There is some pattern there, but the pattern is stronger with the negative 0.9 in that instance. So again, remember that if we want to determine what's the stronger correlation, we look at the absolute value, not the sign. The sign tells you the direction of the movement. Very, very important. So here we can use this following table as kind of a basic standard or basic good practices, if you want, in terms of identifying what is a good correlation statistic and what is a weak correlation statistic, what is a very good correlation statistic, and what is a non-existent correlation statistic, if you want. So here, if we look at the size of the correlation being anywhere between a 0.8 to a positive 1, and again, you'll notice here, I do not include anything in regards to or a reference to positive and negative, because again, that doesn't really matter to us because we're only talking about the strength of the relationship in this particular case, not the direction of movement. So in our particular case, if we have a value of 0.8 to a value of a 1, we have a very strong relationship. 0.6 to 0.8, strong relationship. 0.4 to 0.6, moderate relationship. 0.2 to 0.4, a weak relationship. And last 0.2 to 0.0 to 0.2 is a weak to a no relationship. So in other words, the closer that your value is, your correlation statistic is to 0, the less of a relationship there is, less of a pattern. In other words, there doesn't really seem to be this logic or this pattern to the movement of our scores. They just seem to be all over the place. So here you can really use this table as kind of good practices in terms of identifying what is a good statistic correlate or a good correlation statistic versus a weak correlation statistic, if you want to think about it in terms of that. Now, the last issue here that I'll be discussing in terms of this lecture is what we call the correlation or the coefficient of determination. We sometimes also call this amount of variability that's explained by our data, and we normally signify this by using the statistic r squared. Now, what is r squared? R squared is the way that we call our coefficient of determination. Our coefficient of determination determines for us how much variability, in other words, variance, is being accounted for by your predictor variable on your criterion variable. In other words, using your x variable, so your independent variable, how much of the dependent variable is being explained by your independent variable. So in other words, we're talking about effect variance. So all semester long, when I've been introducing this idea of effect variance, effect variance, effect variance, I keep telling you it's the numerator, the numerator, the numerator. We actually now can calculate a statistic that we call our coefficient of determination that will tell us exactly, precisely, how much of the variability, so how much of the spread in the scores, the differences in your scores, are actually being attributed to your manipulation or control. That's what the coefficient of determination actually means. How do we actually calculate the coefficient of determination? Very, very easily. The coefficient of determination ultimately can be identified as a percentage or even as a decimal point as well. in the way that you just square your correlation coefficient, and that will give you your coefficient of determination. So if we take, for instance, 0.60 and square that value, that's going to give you 0.36. So in other words, 36% of the variability, so in other words, 36% of the relationship between your x and your y is being explained by your x variable. In other words, your independent variable. This is a great statistic that we have in your textbook. They do a very good job of discussing what the coefficient of determination is using this r-squared value. I would strongly recommend reading over that because it's a very good statistic to know if you want to become a statistician or even a researcher, or even trying to understand how good your manipulation is in terms of its effectiveness for accounting the dependent variable changes. So in other words, that's really what the coefficient of determination is really doing. That it's telling you how much of the change in the y variable is being accounted for by the x variable. The higher that number is, the more is being accounted for by that independent variable. All right, so that wraps up our discussion associated with our correlation coefficient. Again, please do remember to read your book chapter to follow along associated with the correlation coefficient discussion of R. And please email me and let me know if you have any questions.